Welcome, everybody. Good afternoon. It's my pleasure to welcome you to the last of this semester's CVL brown bags, and this may be the last of our sessions this semester, but it's by no means the least. I'm very delighted that we will be having Dr. Mariam Ali talk to us this afternoon. So just a couple of quick housekeeping issues. As usual, please feel free to ask questions on the chat at any time during the presentation, and I'll be fielding those at the end in a Q&A session. But don't wait till the end if you have a pressing question. We'll be monitoring as we go along. And also, you'll get a link during the course of the talk in the chat to allow you to join Mariam and myself after the formal presentation for half an hour or so in a chat room where we can all see each other. So Mariam is an assistant professor in the psychology department at Columbia University in New York. She completed her PhD at UC Davis under the mentorship of Andy Ionlinas and Charan Ranganath, and then went on to a postdoctoral position with Nick Turk-Brown at Princeton, where she was from 2013 to 2017. Then she joined Columbia. She's very well known for her pioneering work implicating the hippocampus, not only in memory, but also in perception, and also for her work on the studies of the intersection between attention, memory, and hippocampal function. And that's what she's going to talk to us about today. So without further ado, it's my pleasure to turn over the proceedings to Mariam, and I look forward very much to the presentation.
Thanks so much, Mick, for the invitation, and thank you everybody for having me here today. I'm really excited to tell you about some of my work exploring interactions between attention and memory in the hippocampus. So I want to start off by having you all imagine that you're faced with a really big problem, like trying to understand the brain. It can be useful if you tried to simplify that problem by breaking it up into a set of smaller problems and then tackled each of those problems in isolation. And that's traditionally how cognitive neuroscience research has progressed. So for example, say that you find that you're really interested in visual perception. You might choose to study the occipital cortex or ventral temporal cortex. Or if, like me, you're really interested in long-term memory, you might instead focus on the hippocampus or the medial temporal lobe cortex. Or if you want to focus on attention, you might turn to the prefrontal cortex. And this approach has been really useful in generating lots of very important insights about the mind and brain. But in my lab, we try to challenge these boundaries. So for example, is it really the case that there is an abrupt transition in the brain between systems that are important for perception and those that are important for memory? Or can perception critically depend on memory systems like the hippocampus? And can attention also extend to these medial temporal lobe memory systems? And the approach that I want to argue for, and my lab's general philosophy, is that we can better understand the mind and brain if we focus on how the representations of any given brain area can allow that region to very flexibly contribute to many different components of cognition. So in my talk today, I hope to be able to convince you that the hippocampus, rather than being a dedicated memory system, is one such brain area whose representations, and particularly its flexible relational representations, allow it to critically contribute to attention and perception, as well as memory. So this talk will be about attention, perception, and memory. So before I dive in, I want to give a quick real-world example of how these different parts of cognition might interact with one another and how they might operate. So I want you to imagine that you are in an art museum and you find that you are surrounded by paintings. But you'll also notice other things. There's all those decorations on the wall, and there's different pieces of furniture. So given all of that, how are you able to process this complex environment? Well, if you find that you're really interested in art, you might choose to direct your attention to a particular painting on the wall. And once you do that, attention will change the way that you perceive the painting by enhancing the representation of its features in your visual cortex. And attention will also affect your memory. You're more likely to remember the things that you pay attention to than things that you don't. So attention, perception, and memory interact, but what I want to challenge is the idea that they might depend on separate, dedicated systems in the brain and operate with different functional principles. And instead, I'd like to make the argument that common functional principles and common neural representations can help us understand these different aspects of cognition. And the way I'll do that is by using the hippocampus as an example and showing you how its flexible and relational representations can allow it to critically contribute to attention and perception, as well as memory. So to that end, I'll go over 3 lines of research. So in the first part of my talk, I'll ask, how does attention create memory? In the second part of my talk, I'll ask if the hippocampus can play a necessary role in attentional behavior, and if so, how? And then finally, I'll ask how we can use our long-term memories to guide attention. So first, how does attention create memory? We know that attention is critical for memory at the level of behavior. So the way that you direct your attention will of course influence what you can remember later on, but how does that happen mechanistically, and how does that happen in the brain? Well, there are at least 2 potential routes by which attention might affect your memory. So first, we know that attention has really strong effects on the visual system. So if this arrow represents the flow of information from occipital cortex into ventral temporal cortex, then one possibility is that attention will simply strengthen those representations, and that makes those representations more likely to be transmitted to the hippocampus, and then they can be encoded into memory. But there's an alternative possibility, which is that attention might directly modulate the hippocampus itself. So in a couple of different studies, we first asked, how does attention modulate the hippocampus? And if it does, what are the implications of that for what we can encode into our episodic memory? So how does attention modulate the hippocampus? Well, some previous studies that have examined that question have surprisingly found that attention does not seem to affect the overall level of activity in the hippocampus during online processing. And we hypothesized that these null effects might arise for a couple of different reasons. So one thing that we noticed is that these prior studies tended to manipulate attention to individual items, but we think the hippocampus is particularly critical for processing the relations within and between items. And second, these prior studies focused on the overall level of activity in the hippocampus, but work from animal models has suggested that attention might instead affect the stability of activity patterns in the hippocampus. So we hypothesized that in a task that requires relational representations, the hippocampus would show distinct patterns of activity for different attentional states. So to test that hypothesis, we designed a task that we've been calling the art gallery task. And the idea with this task was to try to manipulate attention to relatively high-level relational features, which we know from memory research are a really important aspect of hippocampal representations. And when I say relational features, what I mean are representations of multidimensional components of any given environment. So in these examples, that would be representations of visual associations or visuospatial associations. So the task looked like this. On every trial, participants viewed a base image, which was a room that was rendered in 3D. It had multiple different pieces of furniture, different wall angles, and a single painting. And we told people before each trial whether they should pay attention to the art or to the room. So on art trials, participants had to attend to the artistic style of the paintings. So that would be things like the use of color, the type of brushstroke, and the overall amount of detail. And on room trials, they were instructed to pay attention to the spatial configuration of the room, so both the layout of the furniture and the angles of the walls. Then, after the space image, participants viewed a search set of 4 other images. On art trials, they had to search through that search set to see if they could find a painting that could have been painted by the same person who painted the painting in the base image. So they were looking for a painting that was similar in terms of its artistic style, even though the content might be different. Then on room trials, participants had to search through the search set to see if they could find a room that had the same spatial configuration as the base image, but viewed from a slightly different perspective. And critically, everything else about the base image and its matching room was changed. So the wall colors were changed, chairs were swapped with different chairs, tables were swapped with different tables, but the arrangement of those elements was the same. And then at the very end of the trial, participants just had to respond yes or no as to whether they found a match in the probe dimension. So there are 2 key aspects of this design that I'd like to bring your attention to. The first is that we used the same exact stimuli in both attentional states, and this allows us to isolate effects in the hippocampus that are related to participants' top-down attentional states rather than differences in bottom-up stimulation. And second, low-level visual information was not especially useful in either task, and we thought that would make these tasks more likely to engage those relational representations of the hippocampus. And specifically, we thought that the art task might draw on relational representations because participants had to attend to multidimensional features of the paintings, so things like the brushstroke and the use of color, and relate those features to other paintings. And the room task might require those relational representations because participants had to attend to multidimensional features of the rooms, so the arrangement of furniture and the wall angles, and relate those features to other rooms. And again, we hypothesized that if these tasks effectively engage the relational representations of the hippocampus, then attention to artistic style versus room layout might create distinct patterns of activity in the hippocampus. So to test that hypothesis, we had people do this task while they were being scanned with high-resolution fMRI, and then we examined activity patterns in the hippocampus as a function of participants' attentional states. And consistent with our predictions, we found that the hippocampus did contain distinct patterns of activity for the art and room attentional states. And when we compared those 2 attentional states directly, we found the activity patterns in each hippocampal subfield were more similar across different room trials compared to different art trials. We also found that in the CA2, CA3, and dentate gyrus subfields of the hippocampus, the individual differences in how stable the pattern of activity was in the room attentional state predicted how well people did on the room task. So together, these results suggested a few things to us. So first, we found that attention does modulate the hippocampus. Second, we found that this modulation of the hippocampus by attention is meaningful for predicting people's online, in the moment, attentional behavior. And finally, the hippocampus might have a special role in spatial relational attention. So from that first study, we found this novel signature of attention in the hippocampus, which was the creation of state-dependent patterns of activity. We then conceptually replicated that effect with a very different paradigm in which we examined attention to size relations, spatial relations, and temporal relations. And then in a follow-up study, we examined the consequences of these attentional states for subsequent memory. And here we found that the quality of hippocampal attentional states during encoding predicted memory for goal-relevant information. So what that means is that on trials in which the hippocampus was in a really good art attentional state during encoding, participants were later more likely to remember unique features of the paintings that they had been looking at, whereas on trials in which the hippocampus was in a good room attentional state during encoding, participants were subsequently more likely to remember unique visual features of the rooms that they were looking at. So far we have some insight into how attention might create memory. So we found that attention can change the state of the hippocampus, and the hippocampus was then able to prioritize goal-relevant aspects of experience for encoding into memory. But of course, you'll have noticed that the work I've shared with you so far has come from fMRI studies, and fMRI studies can generally only provide correlational evidence. So if I want to make the argument that the hippocampus actually plays a necessary role in attentional behavior, then I'd have to examine what happens to attention when the hippocampus is damaged. And my former research assistant, Nick Ruiz, did exactly that. So if the critical aspect of hippocampal function is its relational representations, then we'd expect that hippocampal damage would impair relational forms of attention. So to test the prediction that the hippocampus might be essential for relational attention, we used a modified version of the art gallery task that I've been telling you about. We simplified it so that there were only 2 images presented on each trial, and that was to make the task more feasible for patients with hippocampal damage. So we had 4 types of trials. The first 2 are the trials that you're already familiar with, and the purpose of these trials was to try to engage the relational representations of the hippocampus, and I will refer to these as similar trials. So on each trial, participants viewed 2 images, which were again these rooms that were rendered in 3D, each with multiple pieces of furniture, different wall angles, and a single painting each. On similar art trials, participants had to judge if the 2 paintings could have been painted by the same artist, yes or no. So for example, on this trial, the participant might say yes, because these 2 paintings have a very similar artistic style. On similar room trials, participants had to judge if the 2 rooms had the same spatial layout from a slightly different perspective, yes or no. And again, on this trial, the participant might say yes. And we know from our past fMRI studies that the hippocampus can discriminate between these 2 attentional states and that its activity can predict behavior. The other trial types were control trials, which we did not expect to require the hippocampus because they placed fewer demands on relational processing, and I'll refer to these as identical trials. So again, individuals viewed 2 images on each trial, but this time they simply had to detect repetitions of identical paintings, like in this example here, or repetitions of identical rooms, like in this example here. And the idea is that this task can be accomplished really easily on the basis of representations in visual cortex without any need for hippocampal relational processing. So to summarize our task, we had similar trials and identical trials, and within each of those we had room attention and art attention. And there's a couple of different predictions that you could make. So one prediction is that the hippocampus is critical for any task that requires relational representations, and that would be consistent with many different models of hippocampal function. And if that's the case, then you might expect hippocampal damage to impair performance on the similar room trials and the similar art trials, but leave performance on the identical trials unaffected. But there's an alternative hypothesis, which is that hippocampal damage might only impair performance on the similar room task, and that's because in our past fMRI studies, we've always found that the hippocampus is much more strongly modulated by the similar room task and predicts behavior best in that similar room task. And that would also be consistent with models of hippocampal function that emphasize that it's particularly important for spatial processing. And it would also be consistent with findings that damage to the hippocampus can impair the perception of complex scenes, but not complex objects. So to examine those hypotheses, Nick tested 7 patients with medial temporal lobe damage, as well as 14 healthy age and education matched participants. So here I'll show you the data for the healthy participants as the filled in circles and data for the patients as the open shapes. One patient had bilateral hippocampal damage following a hypoxic event, So he'll be shown as the open diamond, and the rest of the patients had unilateral temporal lobectomies for the treatment of intractable epilepsy. So they had more extensive damage that included the hippocampus and the surrounding medial temporal lobe cortex on one side of the brain. And I'll show you behavioral performance in terms of A prime, which is a non-parametric version of D prime. So it's a measure of behavioral sensitivity, where 1 would indicate perfect performance and 0.5 would indicate chance. So we found no difference between the healthy participants and the patients on identical art trials. There was also no difference between the two groups on the identical room trials, and that's exactly what we expected. Now, intriguingly, we found that the patients were not at all impaired on the similar art trials, but they were significantly impaired on the similar room trials, and in fact, their performance wasn't different from chance levels. Because all of these patients had hippocampal damage, and the damage outside of the hippocampus varied across patients, we can infer that the hippocampus, or the medial temporal lobe more generally, can play an essential role in at least some components of attentional behavior, and particularly spatial relational discriminations. So from the study, we have some evidence that the hippocampus or the medial temporal lobe more generally can play a necessary role in some aspects of attentional behavior, and particularly the spatial relational discriminations that we taxed on the similar room trials. So the second part of my talk here had a two-part question. So I hope I've answered the first part, but the second part now is how. So how can the hippocampus come to play a role in attention or perception? So here, I'd like to tell you about some pharmacological studies in my lab in which we've been trying to determine the neuromodulatory mechanisms of attention in the hippocampus. And this is work that's been done by Nick Ruiz and Monica Tu. So we were really interested in this question because at any given moment, there can be competition in the hippocampus between internal and external sources of information. And specifically, there can be competition between input to the hippocampus about the external world and memory retrieval mechanisms that might instead bias the hippocampus toward processing internally generated sources of information. So to make that more concrete, I want you to imagine again that you're in this art museum and you choose to direct your attention to a particular painting on the wall. But once you do that, the visual features of that painting might trigger memory retrieval of some associated information, like similar paintings that you've seen in the past. So if you want to suppress that memory retrieval in order to better focus your attention on the visual features of the painting that's in front of you, then you'll need to somehow bias the hippocampus toward processing external information. And it turns out that acetylcholine can do exactly that. So to better understand how cholinergic modulation might enhance hippocampal attention, we first have to talk about the hippocampus in a little bit more detail. So input from the entorhinal cortex to the hippocampus is really important for conveying information about the external environment and for encoding new memories. And the recurrent connections in hippocampal subfield CA3 are important for retrieving memories. Acetylcholine enhances the input from entorhinal cortex to the hippocampus and suppresses the recurrent connections in CA3. So this should have the hippocampal representations toward the external world, which is of course important for externally oriented attention. So acetylcholine should stabilize hippocampal representations of the external world, and in that way improve attention and perception on relational attention tasks like the ones that we've used previously. So our specific prediction was that if cholinergic modulation enhances those externally oriented attentional states in the hippocampus, then cholinergic modulation should improve performance on attention and perception tasks that require the hippocampus. And specifically, cholinergic modulation should improve performance on the similar room task because that's the one that we've shown in our past studies to more consistently recruit the hippocampus. You'll have noticed that we initially hypothesized that performance on the other trial types would not be affected by cholinergic modulation, but that certainly doesn't have to be the case, and I'll return to that in a little bit. So in order to test this hypothesis, we had people do the same exact task that we used with the hippocampal lesion patients, but this time we had a pharmacological manipulation. So we had people do this task while they were on a cholinergic agonist, and then again while they were off a cholinergic agonist to see how cholinergic modulation might affect their behavior. So what we did is we found people who voluntarily self-administer cholinergic agonists all the time, and of course that would be cigarette smokers. The critical thing for us was that because they gave themselves nicotine, we didn't have to jump through any hoops with the ethics board, and it made this study really tractable for us to do. So what we did is we had these nicotine cigarette smokers come into our lab for 2 sessions. Both were first thing in the morning. One session was their on session, for which they smoked right before coming into our lab, and then they did our task with the similar and identical art and room trials. Then for their other session, with the order of course counterbalanced, they abstained from cigarette smoking for at least 12 hours before doing our task. We asked them how many cigarettes they smoked to note compliance. People reported smoking 1 to 3 cigarettes for their on session and not smoking at all for the past 12 hours for their off session. But of course, we didn't just take their word for it. We also had them breathe into a carbon monoxide monitor. So carbon monoxide, ppm, or parts per million, provides a measure of how recently or how much a person has smoked a cigarette. And critically, these carbon monoxide levels are fairly highly correlated with nicotine levels in the person's blood. So we could make sure that these carbon monoxide levels were higher for the on versus off session. And again, our prediction was that if cholinergic modulation enhances hippocampal attention, then nicotine cigarette smokers should perform better on the similar room task when they're on versus off nicotine. So here I'll show you performance in the off and on nicotine sessions, with performance again being measured as A'. We found no difference between the on and off smoking sessions for identical art trials. We also found no difference between the sessions on the identical room trials, and also no difference between the sessions on similar art trials. Then finally, but unfortunately, contrary to our expectations, we also found that there was no difference between the on and off smoking sessions for these similar room trials. So here, at least, we found null effects across all 4 tasks. So that said, the on versus off comparison is coarse, and we have more precise information about people than whether or not they smoked because we have their carbon monoxide ppm levels. And again, those tell us how much or how recently a person smoked. So if cholinergic modulation enhances attention, then individual differences in carbon monoxide levels might be related to performance enhancements. So to test that, we calculated 2 measures for each person. So first, we took their carbon monoxide ppm difference between the on and off smoking sessions. And that means that even if someone cheated and smoked prior to their off session, this difference score would still tell us how much more they smoked for the on versus off session. And we also calculated their A' difference between the on and off smoking sessions. So more positive values on the y-axis would indicate greater performance enhancements on nicotine. So if cholinergic modulation enhances hippocampal attention and perception, then the people with the highest carbon monoxide ppm difference should show the greatest performance enhancements, and particularly on the similar room task. And that is exactly what we found. Carbon monoxide ppm differences didn't predict performance enhancements on any other trial type. So this result is consistent with cholinergic modulation of hippocampally mediated attention and perception. So to return to this slide, our hypothesis was partly right, but partly wrong. We did not see a general performance enhancement on versus off nicotine on the similar room task, but we did observe monotonic improvement on that trial type as a function of more nicotine smoking, and that's still consistent with cholinergic modulation of hippocampal attention. We didn't see cholinergic modulation of performance on any other trial type, but again, that certainly didn't have to be the case because we know that nicotine can act throughout the entire brain and it can have effects on visual cortex. So the null effects that we saw on those other trials will have to be investigated further, and I'm happy to talk about that later if you're interested. So now to briefly summarize the second part of my talk, we first found that the hippocampus, or the medial temporal lobe more generally, can play an essential role in at least some components of attentional behavior, and particularly spatial relational discriminations. And we also found that cholinergic modulation from nicotine can enhance that type of attention and perception. So my talk so far has considered attention in a pretty limited way. So we've considered attention in situations in which we just tell people what they should be paying attention to. But that's not typically how attention operates in our real world. So in real life, it's really rare to get moment by moment instructions on how you should be directing your attention. And instead, our attentional states are often guided by our memories of past experiences. So now in this last part of my talk, I'd like to tell you about some work in my lab related to how our long-term memories can be used to guide attention. So I first want to consider these forms of attention in a bit more detail, and I want you to imagine that you're in a situation where you're driving to one of your favorite art museums, and in my case, that would be the Barnes Foundation in Philadelphia. So you might observe a sign which provides you with an external and explicit cue to pay attention to the right in order to find your art museum. But alternatively, you might be driving down the street and there is no sign. So you would instead have to call on your memory for the buildings that you drove past to figure out if you're on the correct street, which direction you came from, and then use that to infer whether you should pay attention to the left or to the right. So the basic idea here is that our attentional states can be guided either by external cues in the environment or by our internally retrieved memories. Kianobre, Mark Stokes, and their colleagues have shown that memory-guided attention compared to environmentally cued attention is associated with increased levels of activity in the hippocampus. And they've also found that this increased hippocampal activity for memory-guided attention can be observed as soon as information from memory is available and even before an attention task begins. So the idea here is that you can call on your hippocampal memories to bias your attention one way or the other, and that biasing process can happen even before an attention task starts. We also know that hippocampal activity patterns can represent your online or current attentional state. So the content of hippocampal representation can reflect attentional states that are currently active. And then finally, a rich body of work has shown that the hippocampus is important for many different aspects of memory-guided, goal-directed behaviors, perhaps through its interactions with the medial prefrontal cortex. So together, these lines of work suggest that the hippocampus, perhaps with MPFC, might be important for guiding attentional behaviors on the basis of memory. So in this study, we wanted to ask how the hippocampus and MPFC might support memory-guided attention. So to address that question, my former postdoc, Irene Goncelli, compared attention in two tasks that differed only in their demand to use memory to guide attention. We expected to be able to replicate past studies in showing that hippocampal activity is higher for memory-guided compared to environmentally cued attention. And given the importance of hippocampal MPFC interactions for memory-guided behaviors more generally, we also expected the MPFC would show higher levels of activity for memory-guided compared to environmentally cued attention. But the problem with this is that enhanced overall activity levels are ambiguous, so they cannot by themselves tell us how a brain region is supporting memory-guided attention. So for example, it could be the case that the hippocampus just retrieves a memory, and that other brain areas actually use that memory to guide attention. Or it could be the case that the hippocampus can actually represent the attentional goal itself. So if you were to think back to that driving example, that difference would be between the hippocampus just retrieving a memory that the art museum is on the right, versus the hippocampus actually representing an attentional bias towards the right-hand side. And because we know from past studies that the hippocampus can represent your current attentional state, then it's very possible that it also might represent attentional states when they are retrieved from memory. So to test that, we used pattern similarity approaches to test the prediction that the hippocampus and MPFC will prepare for upcoming attentional states when those attentional states are guided by memory, and that they would prepare by actually representing the attentional state that has to be used in the future. So if we were to go back once again to that driving example, the idea is that hippocampal and MPFC activity patterns would contain information about a rightward attentional bias, if that's what your memory tells you that you should do, and even before you start paying attention to the right. So to test those hypotheses, Irene designed a memory-guided version of the art gallery task that you're now incredibly familiar with. So in this memory-guided version, we first had participants memorize a set of stay and switch cues. And these cues told people whether during the subsequent attention task in phase 2, they would have to stay in the same attentional state on the next trial or switch to the other attentional state. So participants memorized an art stay cue and an art switch cue, and a room stay cue and a room switch cue. And these stay and switch cues would only be presented in the attended dimension. So that means the art stay and switch cues only appear on trials where art is attended, and room stay and switch cues only appear on trials where rooms are attended. So to make that more concrete, here is the task that you're already familiar with. Participants viewed a base image followed by a search set, and their main task was to look either for paintings that could have been painted by the same artist or rooms with the same layout from a different perspective. So this is the task that you're already familiar with. The new thing here is how the attentional cue was selected on each trial. So on the very first trial, participants were free to choose what they wanted to pay attention to, so they could choose art or room, and say here the participant chose room. But after this first trial, participants had to monitor the search set for stay or switch cues, which could appear anywhere in the search set, and then they had to use the stay or switch cue to select their attentional state for the next trial. So this example is a room trial, and here I've highlighted a room stay cue. So that tells the participant that they have to stay in the same attentional state on the next trial. So on the next trial, they should select room as their attentional state. Alternatively, this trial could have contained a switch cue, which would tell the participant that they need to switch to the other attentional state on the next trial. So on the next trial, they should select art as their attentional state. So this task requires people to memorize the stay and switch cues and what they mean in order to select their attentional states. The comparison condition was the art gallery task we've used in the past, which now I'll call the explicitly instructed condition. And this condition is explicitly instructed because the attentional cue was randomly assigned at the beginning of each trial in the form of an explicit instruction. So we just told people to pay attention to the room or pay attention to the art. So to briefly summarize those two tasks, they had identical stimuli and they had identical motor demands. So the only difference between them was the memory-guided task required people to remember the stay and switch cues and what they meant in order to select their attentional states. So we first examined overall activity levels for the two conditions, and consistent with our predictions, we found that both hippocampus and MPFC showed higher levels of activity for memory-guided compared to explicitly instructed attention. And we also found that individual differences in how much hippocampal activity was elevated for memory-guided attention were correlated with individual differences in how much MPFC activity was enhanced for memory-guided attention. And this suggested to us that these two regions might be working together or at least engaged in a similar function. So now with this result in hand, we next wanted to establish exactly how the hippocampus and MPFC might support memory-guided attention. And again, we expected that these regions would represent upcoming attentional states, and primarily when they were guided by memory. So here's how we tested that. As a brief reminder, this is the trial structure that you're already familiar with, and now I'll break it down into two components. The image period is when the images are on the screen and participants are actively paying attention to either artistic style or room layout. The orienting period is when participants are pushing a button to initiate the trial and seeing the attentional cue. In the explicitly instructed condition, participants just push 1 or 2 to start the trial, and then their attentional cue is randomly assigned. Whereas in the memory-guided condition, participants have to select their attentional state based on their memory for the preceding trial. And we predicted that during that critical orienting period, the activity patterns in the hippocampus and MPFC would resemble the attentional state that is coming up in the image period, and primarily when that attentional state was guided by memory. So here's how we tested that. First, in hippocampus and MPFC, we obtained mean patterns of activity for the art and room attentional states from the image periods, and I'll call these templates for the two attentional states. And what these templates tell us is what brain activity generally looks like when participants are actively paying attention to artistic style or room layout in the images. We then obtained activity patterns for each individual orienting period, and we correlated the orienting period activity patterns with the attentional state templates from the image periods. So say this is an orienting period in which room is the attentional cue. We would take that orienting period activity pattern and we would correlate it with the template for the same attentional state, which in this example would be the room template. And we would also correlate the orienting period activity pattern with the template for the other attentional state, which in this example would be the art template. And then finally, we'd compare those correlations to one another. So if the correlation with the same state template is higher than the correlation with the different state template, that would tell us the activity patterns in that brain region during the orienting period actually resemble the upcoming attentional state more than the other one. So this gives us a type of preparatory signal. And we expected that the hippocampus and MPFC would show that effect, and primarily for the memory-guided condition. So here I'll show you the correlation with the same state template minus the correlation with a different state template. So more positive values here would indicate more evidence for the attentional state that is coming up, and more negative values would indicate more evidence for the other attentional state. So we found that in the hippocampus for the memory-guided task, the activity patterns during the orienting period did in fact resemble the upcoming attentional state more than the other one. This effect was also seen when attention was explicitly instructed. However, that preparation signal was significantly stronger when attentional states were guided by memory. In MPFC, we found the activity patterns during the orienting period resembled the upcoming attentional state more than the other one for both conditions, but here there was no statistically significant difference. So the hippocampus and MPFC do prepare for upcoming attentional states, and they prepare by actually representing the attentional state that is about to be used in the future. And in the hippocampus, that preparation signal was significantly stronger when attentional states were guided by memory. So now to briefly summarize my talk, I first showed you that attention stabilizes patterns of activity in the hippocampus, and the stability of those representations predicts both online attentional behavior as well as encoding into episodic memory. We next found that the hippocampus, or the medial temporal lobe more broadly, can play an essential role in at least some aspects of online attentional behaviors, and particularly spatial relational discriminations. And we also found that cholinergic modulation from nicotine can enhance that type of attention and perception. And then finally, we found that hippocampus and MPFC are modulated by memory-guided attention and prepare for upcoming attentional states. All right, so I've shared a few experiments related to this interplay between attention, perception, and memory. So now I just want to conclude by revisiting the point I made at the beginning of the talk. So again, I think it's been incredibly valuable to divide up the brain into distinct components and analyze their function in isolation. But ultimately, we know that cognition is the result of the interplay between these different components. So I think that one very fruitful way of doing research moving forward is to think about the representations of any given brain region and how those representations can allow that region to flexibly contribute to many different components of cognition. So I hope that in my talk today, I've been able to convince you that the various representations of the hippocampus allow it to critically contribute to attention and perception, as well as memory. I'd like to wrap up by thanking my lab, particularly Nick Ruiz, Monica Tu, and Aren Vincelli, who did the work I told you about today. I'd also like to acknowledge my funding sources, and of course, I'd like to thank you for your attention, as well as your perception and memory, and I'm happy to take any questions.
Thank you so much, Mariam. That was wonderful, beautifully clear, really interesting work.
Thank you.
Thank you. So we have some questions. I will give them in the order that they came in rather than the logical order of your talk.
Sure.
One question concerns the smoking study. Two components to it. Firstly, using smokers to try to enhance acetylcholine may have more to do with depleting stimulation when they withdraw from smoking than enhancing it when they smoke, because of desensitization of cholinergic receptors that comes with particularly heavy smoking, habitual smoking. That's one issue. The second issue related to the same study is that there's cholinergic receptors all over the brain. It's really not clear how a psychopharmacological study could narrow down any effect that was found to the hippocampus.
Sure. So to those are both really excellent points that we've both thought about a lot. So for the first question, that's absolutely true. And the way that we tried to avoid that is by only testing people who were very light cigarette smokers. So we administered a questionnaire that tested for nicotine dependence, and everybody scored in the low or low to moderate range. And there's been literature showing that people who are very light cigarette smokers don't show withdrawal effects when they're abstinent. So for this reason, we think it's unlikely that the effects that we're seeing are driven by withdrawal symptoms, and we avoided testing heavier cigarette smokers for at least that reason.
Right.
For the second question, you're absolutely right there as well. We wanted to do an fMRI version of the nicotine smoking study where we test the smokers in an off session and an on session to compare hippocampal activity patterns for the two conditions. Unfortunately, COVID happened, and so that was put on hold for a while. You're right that we can't definitively say from that study that cholinergic modulation is affecting hippocampal functioning. It's only consistent with what we would expect based on hippocampal modulation. So we can say that this result is supportive of our prediction. The cholinergic modulation should enhance hippocampal functioning, but of course we can't rule out that it's also affecting functions in other brain areas. The fact that it was a relatively selective effect on the hippocampally mediated task and that performance didn't correlate with nicotine levels across all 4 tasks suggests that maybe cholinergic functioning is particularly important for complex hippocampal tasks, at least in our hands with this manipulation. But of course, to more definitively answer your question, we'd want to do a parallel fMRI study as well.
Yeah, thank you. So another question, this relates to the study of the patients with hippocampal lesions. And here, the question is whether or not these effects really, I mean, you addressed this to some degree in your talk, but to what degree do you think that the very extensive lesion that you get with typical temporal lobectomy may have encroached on parahippocampal cortex? And so the reason why you see the selective effect for room or scene condition is because you're hitting somewhere like the edge of the parahippocampal place area rather than the hippocampus per se.
Yeah, that's a great question. So for those patients that had temporal lobectomies, it was mostly the anterior parahippocampal gyrus that was affected. So it was mostly the anterior hippocampus and the perirhinal cortex. The parahippocampal cortex and PPA were largely spared, although we should have confirmed that with volumetric analyses, but we didn't. But they were relatively more spared than the anterior hippocampus and perirhinal cortex. And of course, in the hypoxic patient, that patient didn't have any noticeable lesions to the parahippocampal cortex at all. We think he had some volume reduction in striatal regions, which is sometimes observed with hypoxia. Yeah. But there was no notable parahippocampal damage in that patient. And as you can see here, he's the diamond, and he shows the same effect that all the other patients show. So we think it's unlikely to be driven by PPA damage for those reasons.
Yeah. Very good, thank you. So I've got a question here, which I'm going to slightly reframe, but it relates to aging and the extent to which do you think, if I generalize this from the way the question is framed, the extent to which you would see similar results in older individuals? Obviously, that's of great interest to us in our center here.
Yeah, we actually started testing a larger group of older adults to answer that question in particular. We found hints that the similar room task is more susceptible to aging than the other tasks. Of course, brain damage to the medial temporal lobe additionally impacts it above and beyond that because we had age-matched controls in this study. But at least from our preliminary work, we tested maybe 20 older adults or so before we had to pause things for COVID. It seemed like that task was a little bit more susceptible to declines with healthy aging.
Would you expect to see the same sort of fMRI effects, though? For example, in your last experiment looking at memory-guided attention, there's no reason, I suppose, I mean, I don't think there's any reason why you wouldn't see a very similar set of results.
In terms of aging affecting the room task?
Like pattern similarity analysis, the implicated brain regions and the like.
Yeah, I think I would expect the same thing there. The memory-guided task has these additional demands on episodic memory that might hurt performance more broadly than just the room task. But if we were just to focus on behavior and pattern similarity for the main attention task, then I would expect the same thing there as well.
Yeah. Great. I've got a question here asking whether, do you think that studies of adult ADHD might be informative of the phenomena you've been looking at, modulation of the hippocampus by attention?
Yeah, that's a really great question. And actually the grant that funded the nicotine study was directly inspired by clinical applications to populations like ADHD, with the idea that one problem with ADHD might be disrupted processing of the internal versus external environment. So if this balance between internally generated memories and externally oriented perception is awry, then you might have disordered external attention, so too much attention to the external world at the expense of being able to focus on internally generated information. There's also evidence that there are hippocampal abnormalities in ADHD, and that some people with ADHD can improve with cholinergic drugs, including nicotine. So that was one reason why we were interested in looking at this balance. So we haven't done any studies yet with ADHD, but it's something that we're interested in.
Very cool, thank you. There's a question here. Again, I will slightly paraphrase it, but essentially it comes down to the extent to which your use of pictures may have engaged affective and emotional mechanisms, particularly aesthetics, attraction, and the like.
Yeah, that's a great question. So particularly the art task, we think might be calling on those types of aesthetic representations. If you just do a whole brain univariate analysis looking for regions that show higher activity for the art task compared to the room task, you see regions like amygdala, orbitofrontal cortex, and other regions that are implicated in kind of aesthetic processing generally. So I think you're completely on target there. We haven't really dug into that any further than that, but if you have ideas, I'm curious to hear.
Okay, it's not me who's completely on target. It's the anonymous person who asked the question. I'm happy to take the credit. So one last question, and then we'll be switching to our chat room. In this case, someone who's interested to know whether the similarity of brain activity to the new attentional versus old attentional state, the difference in pattern similarity in hippocampus and MPFC, did that change from early in the orienting period to the end of the orienting period?
That's a great question, and I wish we had the temporal resolution to test that, but we barely have enough temporal resolution in fMRI to test this prediction at all. So
yeah, and there's a follow-up question to this. Did you implement any behavioral measures to test for attentional switching ability to correlate with the corresponding functional changes?
Sure. Yeah, so we actually trained people pretty extensively to be able to use the stay and switch cues to select the right attentional state. So they did training the day before, but they were incredibly accurate because of this overtraining. So they were maybe 95% accurate, which doesn't leave us enough room for looking.
Right. Very good. It's an interesting question for the future.
Definitely.
So, all righty, we're just about out of time with our hour of formality. Let me thank on behalf of our audience, everybody in the virtual room, Mariam, for a wonderful talk, which stimulated a lot of questions and a lot of interest. And I invite anyone who has the time to leave this meeting and to connect with the it's here now, the link that's been posted in the chat room. So I will see you shortly.
Great. See you soon.